Okay, so what does LASSO do for you? LASSO regularization. Regularization. Models. F hat. X vector. So again, LASSO is just another method of model fitting. It is a type of F hat that we can fit to training data. So I should say Y hat equals that. LASSO regularization methods allow you to do two things. In a nutshell, they allow you to do two things. A, allow you to perform, all right, two things. A, parameter shrinkage, meaning we can shrink the values of all our beta hats to 0. Parameter shrinkage. When I say shrinkage, I mean shrinking to 0. But relatedly, another thing that LASSO regularization buys you is variable selection. What do I mean by variable selection? Now, if you're fitting a regression model with 1 or 2 predictors, you know, whatever, that's not that big, that's not really that large a number of predictor variables to consider. But let's say you have 10 million predictor variables to choose from. Do you really want to be fitting a model with all 10 million predictor variables? Maybe, maybe not. Maybe sometimes you only want to pick out a subset of those 10 million predictor variables. So what do I mean by variable selection? It's like of a set x1 through xp, all right? Of a set of x1 through xp predictor variables, select only a subset of them that have high predictive power. Select only a subset of them that have high predictive power. So, parameter shrinkage, variable selection. And again, typically, let's bust out the color chalk, where you would use a variable selection method is when P, number of predictors, is very large. All right. Now, before we jump into the code in lasso.rmd, there's one thing that I want you to keep in mind beforehand. That, if you remember, and you know what, I erased this, so maybe, no, I won't rewrite it, but actually, no, I will. Remember, for cart, we had, what was it? Complex trees versus simple trees. And what set the balance between these two was lambda. Lambda allowed you, by setting that lambda parameter, all right, you could balance between complex models and simple models. And if you recall further, how did we choose the quote-unquote optimal level of complexity, well, you did that using, say it with me now. Actually, you know what? Here's a hint, folks. What is it? It starts with a C and ends in Ross validation, cross-validation, all right? That's how you figured out what the optimal lambda is. And how did you do that? Well, you know what? Let's get back to a recap of cross-validation later. But for now, let's just focus on the LASSO method. Similarly, what does LASSO do? What does LASSO do? So let me draw this over here. LASSO balances between the naive y hat equals y bar regression model versus multiple regression models. You're going to set an optimal complexity level balancing between the absolute most naive model, which is y hat equals y bar, versus a full-on multiple regression model. And what parameter are you going to set to balance between those two? What dial? Lambda. It is the exact same principle, folks. You have alpha versus lambda. Alpha, lambda. Let's now jump into some code. So now, let's knit the LASSO document. Let's open that over here. Okay. Remember that value, folks, the naive model, all right? The naive model is a model where y hat is equal to y bar. In fact, if you fit a regression with only an intercept, b hat or b naught hat is going to be equal to the mean of the y's. So you can think of this as a minimally viable model. We have seen this before in regression. That at its the simplest possible model, on the one hand, is where y hat is equal to the average of the y's. In other words, it's a regression where you only have a fitted intercept, $520. Recall as well down here with our multiple regression model. Now we're going to use all two predictor variables we have, income and limit. Now this might seem kind of ridiculous. Why are we only choosing between two predictor variables? Well, we're going to see later on much more complex situations where the number of predictor variables we have to choose from is much larger than two. But before we get into the nitty-gritty of how LASSO works, let's play with our Shiny app. So now, what we're setting here are log 10 values of lambda. So when log 10 is equal to 1, or I should say log 10 of lambda is equal to 1, lambda is equal to 10 to the 1, in other words, 10. For this particular value of log 10 lambda, in other words, lambda, this is where we're at. Now, this value here is the fitted value. Actually, you know what? Let's do the following. Let's set the value of lambda to be really small. The value of lambda is now represented by this vertical line. What are the fitted slope coefficients and intercept coefficients for this particular value of lambda? Right here. Negative 385, negative 7.6, and 0.26. Notice how for this particular value of lambda, the LASSO estimates match the multiple regression estimates. This is in fact the most complex model. But now, let's set lambda to be really large. This is the least complex model. Complexity is penalized. In fact, at this point, look at the values of income and limit. They're both 0. The only value that remains is the intercept. And recognize that number, folks. What we have here is $520.01. It is the average of the y's. In other words, if you fit a regression with only an intercept term, the intercept will be equal to the average of the y's. So that is the other extreme of the least complex model. But now let's set lambda to be somewhere over here. Okay, maybe right about, okay, I like that. So check it out, folks. For this particular value of log 10 lambda, in other words, lambda equal 10 to the 2.15, all right, the red value, which is income, is now 0. But the value of the slope for limit is not 0, it's 0.11. But what does it mean for the slope for income to equal to 0? It means effectively we've removed income from our model. We've performed variable selection. We have removed income and we are only left with limit. Now again, you might be saying, hey, big deal, we only had 2 variables to choose from. But what we're going to see later on is a situation where we have many more variables to choose from. So now let's ask ourselves what happens at a particular lambda value. Let's set lambda, log 10 lambda to be equal to 1. So where is that? Right here. Okay, great. For log 10 lambda equal to 1, or lambda equal to 10, the LASSO estimate of the intercept is negative 348. Here's the intercept, here's the value of the slope for income. Here's the value of the slope for limit. Notice how they differ slightly from just the plain old multiple regression estimates that are over here. Let's ask ourselves what happens at that particular value of lambda. This is the equation to predict credit card balance. It is that intercept plus this slope for income plus this slope for limit. But where did these values come from? How were they computed? We're now going to pick apart the optimization formula at the root of LASSO. Now I'm going to tell you right now, folks, that it is actually quite similar to the optimization equation from CART. For this, let's go back to the blackboard.